Hello, my name is Chase and I will be doing problem 7.22 for Dr. Cho's System Dynamics and Vibrations class. This homework problem is coming from her homework 11, and this problem is going over the mass flow rates of liquids going into one tank, and that liquid is going from this tank into another, which is going out into somewhere else. For this problem, we know that we're going to have two hydrostatic equations, which is going to be P1 equals to the atmospheric pressure plus the gauge pressure, and then P2 is also the same, but the difference in these two equations is that we have two different heights of the liquids in the tanks. We will have two mass conservation equations. The first one is going to be for the first tank, which is going to have a mass flow rate coming in and out of it, which we can write as QMI1 minus QMO1, which means that the mass flow rate of tank 1 is coming in, or QM1 is the mass flow rate of the tank the liquid going in, and QMO1 is the mass flow rate coming out of the tank. Same thing for tank 2, but we notice that we have the mass flow rate from tank 1 coming out going into tank 2, and then we have another mass flow rate coming out of tank 2, which we don't know. So we will know that these two values will be the same thing in our two equations. We can write the elements of the system as R1, R2, C1 and C2, which is resistors 1 and 2, and capacitor 1 and 2, which the capacitors are the tanks themselves, and the resistors are these throttling valves. We can write the equation for resistor 1 as P1 minus PA equals R1 times the mass flow rate coming out of that resistor, which is going to be QMO1. And we can see that our pressure going into the valve is P1, and the pressure coming out of this valve is PA. For our resistor 2, it's pretty much going to be the same idea as resistor 1, but we're going to have P2 going into that resistor and PA coming out. And that's going to equal R2 times the mass flow rate of QMO2. For these two equations, we know that we have P1 and P2 up here from our hydrostatic equations, which we can plug into these two equations to rearrange to solve for the mass flow rates coming out of each tank. For our capacitors, we'll have the mass flow rate equals the derivative of the gauge pressure, which we can rearrange as PA times dH dt, which that's just going to be the derivative or the change of the height of the water in the tank as time passes. So we'll take all of these elements and combine them together from the mass conservation equations that we laid out at the beginning of the problem. So we can see that this is our first mass conservation equation, which we know that MS1 or m.s1 is from the prior page, which will become this, and QMO1 is going to be PGH1 all over R1. We can rearrange this into this form and then multiply both sides by R1 divided by pH to get our first governing equation. We'll do the same idea with the second mass conservation equation, which we know what m.s2 is and QMO2 is. We'll plug that into the equation, rearrange as well, and this is our second governing equation. To create the equivalent electrical circuit diagram, you'll have to look at the figure diagram given. We'll have a mass flow rate coming in to this tank, which will be the capacitor 1, and it will have a resistor 1 in parallel with it, where the atmospheric pressure is grounded, and the pressure that we see right here is at the top of the capacitor. We will have another mass flow rate coming out of the resistor, as we can see, QMO1, which is the mass flow rate coming out of this pipe right here. And it will be going into the second resistor and capacitor in parallel, where you can see the pressure 2 is at the top of the capacitor 2, and the atmospheric pressure is grounded as well. You can see that we will have this QMIN2 right here, which the mass flow rate of this will equal QMO1. And finally, we will have a QMO2 coming out of the top of the resistor too, as seen right here. And that is the equivalent electrical circuit.